So we are in segment 2 of lecture 42, and here again we're gonna utilize all the equations that we have learned so far concerning the energy balance, like dt by dv and dTA by dv, and the other forms as well as the material balance equations and all the equations related that we will see through the design algorithm. And we're going to apply it all on example 8.5. طيب, example 8.5, production of acetic anhydride. Jeffries, in a treatment of the design of an acetic anhydride manufacturing facilities, states that one of the key steps in the vapor phase is the vapor phase cracking of acetone to ketene and methane. So here we have the cracking step, tamam, and here we have the ketene and the methane. He states further that this reaction is first order with respect to acetone. So it's first order with respect to acetone. And that specific reaction rate can be expressed by this Arrhenius equation, where K is in per second and T is in Kelvin. In this design, it is desired to process 7,850 kg of acetone per hour. And what I did here, I converted the kg per hour to mole per second, because we always, it's more convenient to work with mole when you have chemical reaction. So we do this in a tubular reactor. We carry out this reaction in a tubular reactor. The reactor consists of a bank of 1,000 1-inch schedule 40 tubes with a given inner diameter, arranged in parallel, where each tube is 90 centimeter long. So we have the total volume. Tamam? So that means this feed will be divided on 1,000 tube. Tamam? Okay, we will consider 5 cases. In each case, plot X minus RA, temperature, TA, and any other required variable along the volume of the reactor. طيب, let's see case 1. The reactor is operated isothermally. Then case 2, the reactor is operated adiabatically. Case 3, the reactor is surrounded by a heat exchanger where the heat transfer coefficient is 110 joule per square meter per second per Kelvin. And the temperature of the heating medium, TA, is constant at 1250 Kelvin. Then we have case 4. The heat exchanger in case 3 now has a variable TA. The reactant and the heating medium flow in the same direction. Case 5, you guessed it, same as case 4, but the reactant and the heating medium flow in opposite directions. In the last 2 cases, air with this given Cp at a rate of 0.11 mole per second per tube with TA naught 1250 K is available for heating. The inlet temperature and pressure are the same for all cases at 1035 Kelvin and 162 kilopascal respectively. The standard delta H reaction at 298 is given as 80.77 kilojoule per mole of acetone. Tamam? So you can see that delta H reaction is positive, right? Therefore, the reaction is endothermic. Does it make sense? Yes, it does. Yes, it does, because it's a cracking reaction. It's a thermal cracking reaction. So you need to provide a heat to break the bonds. And then we have the Cp for A, B, and C are all given. طيب, which energy balance are you going to use? تمام? Which energy balance are you going to use? This is a good question. So you have different energy balances for the reactor, and then you have for the heat exchanger. تمام? Okay, so let's start writing the required equations, which is going through the design algorithm. So let's start with the design algorithm. Step number 1, writing the design equation. So the design equation, or the mole balance for a plug flow reactor, is dx by dv equals minus Ra over Fa naught. Tamam? Okay, so we're gonna need this equation, and we're gonna also need the initial conditions, which is at V equals to 0, X equals to 0 as well. Tamam? So let's then frame these equations, because we're gonna plug them into the polymath. Okay? طيب, step number 2. So what variable did I introduce here? Well, it is the minus Ra. That's a variable that I introduced. We need to provide an equation for. Which take us to step number 2, writing the rate law. It says first order with respect to acetone. So K times Ca. Tamam? Okay, very good. So we wrote the rate law, and we wrote the rate law. What variables do we have? We have K and Ca. Ca will take care of it in the stoichiometry. K we need to take care of now. So let's write an equation for K. K equals, it was an Arrhenius equation, right? Over RT. Tamam? Okay, very good. Once we wrote the Arrhenius equation, طبعا the value of A and minus E over R all given in the problem statement, we see that we have T. T is a variable. So now we need to write an equation for T. That means we need to use an energy balance. So we had like 5 of these guys. Which one you are going to use? Of course, when we solve, Shabab, as usual, we solve like for a generic case. Tamam? So that we solve only one time. We don't have to solve 5 different times, because we have 5 different cases. We solve for a generic case, and then for every case we write what we need specifically. Okay? طيب, so for the generic case, the most general applicable equation is this equation, dt by dv. So let's write it down. However, I'm gonna do a little bit modification on this equation without changing it. It's only alteration. Okay, so let me write dt by dv. dt by dv. Let's write this dt by dv equation. And in this case, we have the reaction is endothermic. The reaction is endothermic, and we are heating. So I'm going to talk about localized heat absorbed by the reaction, and we're going to talk about localized heat transferred to the reactor. Okay, and I want these two terms to be positive all the time. That's why I'm going to do a little bit rearrangement. So I'm going to write U times A first. Okay. Oops. Keeps changing the color without permission. U times A times, obviously, TA minus T, right? as if I multiplied this negative into the bracket. So it became Ta minus T. So I did not really change anything. Hello, what else? Let's look at then the second term. Minus Ra times delta H reaction, of course, at temperature T. Again, did I change anything? Let's see. Minus here, the minus here, if you multiply it by the minus here, we'll have positive, see? So you have here positive Ra and you have positive delta H reaction. Okay, good. So I did not really change anything in the equation. Divided by, tamam. So we have here Fa naught, let me write that down, Fa naught times summation of theta I Cpi. Well, the only component species we have in the feed is actually the acetone A, right? So we'll have only Cpa plus delta Cp times X. So now we have an energy balance. We have an equation for T. Okay, and of course we need to provide an initial condition for me to be able to solve this differential equation. Let's write it down. The initial condition at V equals to 0, T equals T naught, correct? Which is 1035 Kelvin. Okay, let me frame all the equations that I'm going to plug in into the polymath. That is this equation as well, and well, not finally, but the differential equation for T, which is dt by dv, as well as the initial condition. Okay, and let me do one more thing here. I would like to define the localized heat transfer as U times A times Ta minus T, and define the localized heat absorbed by the reaction by minus Ra times delta H reaction as a function of temperature. Okay, and let me also frame that. And again here, just a quick insight. Let's see this together. Ta is larger than T. Therefore, the localized heat transfer will be positive, right? Because I'm heating. And minus Ra is positive. Delta H reaction is positive. Therefore, the localized heat absorbed is positive as well. I always want to have the localized heats positive because I want to compare their quantities, their magnitude. I don't want to compare their direction. I don't want to compare the direction of the heat transfer. Okay, so we are done with the step number 2. Let's now go to step number 3. And oops, actually I'm not done with the step number 2 yet, because I did not ask myself, did I introduce any other variables? Let's see. dt by dv, UA, TA. TA could be a variable, right? In case number 4 and 5. However, I will not provide the equation now because it depends on, the equation depends on the direction of the flow. Tamam? T is a variable. Okay. And of course here, so T is a variable as well. However, I have an equation for, which is the dt by dv. And then minus R is variable, and I have equation for. Delta H reaction is variable. Delta H reaction is function of T. So I have to provide an equation for. How did I know? Well, because of delta Cp. The delta Cp in this case is not 0. You can go ahead and calculate it. Therefore, delta H reaction is not constant. It's a variable. So let me write an equation for delta H reaction. Delta H reaction as a function of T equals the standard delta H reaction at T reference, which is 298 in this case, plus delta Cp times T minus Tr. And I'm going to frame this equation as well. Okay, and then again here, alhamdulillah, I don't have any variable here. Delta Cp is not variable, it's constant, so I'm going to deal with it in the evaluation of parameters. طيب. Let me now go to step number 3. That is writing an equation for Ca. Ca equals Fa over epsilon, and Fa, the function of x, equals Fa naught times Fa naught times 1 minus x divided by epsilon. Is epsilon constant or variable? First I have to ask, which phase is the reaction in? It's a gas phase reaction. Therefore, probably epsilon is variable. And so I write epsilon equals epsilon naught times the 3 correction factors. First one related to number of moles. Second one related to temperature, T over T naught. The third one is related to pressure, which is P naught over P. Tamam? Okay, good. طيب, can I simplify? Yes, I can. Well, it's a plug flow reactor, so this guy can go to 1. Tamam, because I'll assume negligible pressure drop. T is variable, so I have to keep it, and the rest stays the same. Therefore, I'll write an equation for Ca as follows. If you allow me, I'll use the top part. So the Ca now becomes, of course, this guy is Ca naught. Ca naught times 1 minus x divided by 1 plus epsilon x times T naught over T. Correct? Okay. And of course, this is a gas phase reaction. That's why I was able to use the equation of state for the volumetric flow rate correction. Let me frame this equation. Did I introduce any variable? Well, x is a variable, but I have an equation for dx by dv. T is a variable, I have an equation for t as dt by dv. Epsilon is a parameter, I can evaluate it at the end. Okay, let's go to the following step. Type, that is combine and evaluate. Combine and evaluate. Okay, and I'll let the computer to do for me the combining and evaluation, combining of the equations and evaluation of the equations. However, I'll need to evaluate some of the parameters, right? And we can go backward. So what do we need to do? Well, let me tell you what we can do. So we're gonna do the following. We're gonna go backward through the equations, and any parameter that needs evaluation, we're gonna evaluate. So let's start with the CA equations. And the CA equations, I have CA naught. So we have to evaluate CA naught. CA naught equals P naught over RT naught. Tamam? Because it's pure A. So because PA naught equals P naught. So we provide the value for P naught. We provide the appropriate value for R. We provide the value for T naught. Okay? Tamam. What else? We have epsilon. What does epsilon equal? Well, epsilon equals YA naught times delta. So YA naught is already known to be 1 pure A, and delta is calculated from the stoichiometry. Remember, it was 2 molecules for the product and 1 molecule or 1 mole for the reactant. Therefore, epsilon equals 1. Well, epsilon equals 1. So let me write it here. Epsilon equal 1. طيب. What else? We have T naught. We just introduced T naught. Okay, we're done with the CA equation. Let's go backward again. Let's go backward. Okay, let's look at delta H reaction. It was standard delta H reaction at T reference. So we have that delta H reaction at TR given. تمام. Make sure شباب you write it in joule per mole instead of kilojoule per mole. Okay, what else? We need TR. TR, we write it down. We need delta CP. So delta CP is CPB plus CPC minus CPA. Right? Okay, this is how we calculate delta CP. Make sure again the unit is joule per mole per Kelvin. So we calculate this, therefore, or we enter the equation this way, and then we write CPA equals this much, CPB equals this much, CPC equals this much. Tamam? Okay, what else? We're done with this equation. Let's go to the localized heat absorbed, localized heat transferred. For the localized heat transferred, we have value for U, right? Yeah, we have a value for U. What about the value of A? Well, we can calculate that. We can calculate that. Okay, let's go here and calculate the value for A. A equals the cross-sectional area divided by the volume, right? Cross-sectional area divided by the volume. Okay, this is the A for the heat transfer, the cross-section, sorry, not the cross-section area, the surface area divided by the volume, because when it comes to A, we see what is it used for, which phenomena. It's used for the heat transfer phenomena, so we choose the surface area through which the heat is transferred. How do you get the surface area? Well, بسيطة. It is 2 pi r, correct? This is the perimeter, tamam, perimeter times the length. Okay, the perimeter, well, if it's not clear, maybe I can rewrite it. So A equals the surface area. The surface area, basically the surface, let me plot it somewhere. Maybe I can do this here. So this is the plug flow reactor. Looking for this surface area here. The surface area. So you can, the surface area, you can calculate the perimeter, al-muhit, times the length. Times the length. This will give you the whole surface area. Tamam? So it is 2 pi r, that's the perimeter, times the length. What about the volume? What about the volume? Well, the volume is the cross-sectional area times the length. That gives you the total volume. So it is pi, it is pi r square times L. L cancels out with L, and then we have pi cancels out with pi, and this R cancels out with this, so we end up with 2 over R, 2 over R, okay, where R is the inner diameter divided by 2. Okay, so let me provide this equation for A as well. So A equals 4 over the inner diameter, where the inner diameter is known. Tamam. Okay, that's about the localized heat transfer. Let's continue walking backward. So let's see, if A naught, we need to provide if A naught in the dt by dv equation. If A naught, please provide it. What else? CPA, we just wrote it there. Delta CP, we just calculated it. Tamam. What about TA? Well, TA will deal with it later on because it could be variable. And yeah, we need to provide the value for E over R, the one which is in the Arrhenius constant, and Arrhenius equation, and then Arrhenius constant as well. Tamam. And khalas. Now we provided everything we need. So we frame all of these. Let's frame all of these. Okay, طيب. So now that we have all what we need, we go ahead and plug this into the polymath, and I call this file the general case. I call it the general case. And then for case 1, I'll go to the general case, open it, and say save as case 1, and then I go back to it again, open it, and go save as case 2, and so on. Hello? So I'll leave you now. Go ahead and plug in all the required equations. After you hand solve them, write them with your own hand and your own notes. So please do not copy from this slide. Do all the writing, all the equations by yourself. Okay, and we'll meet right after you finish typing these equations into polymath. See you soon.